Ellen, you should probably do the introduction such as there is, but I just want to say I am really happy that Jennifer's giving this talk with us.
Really excited to give this talk. Thanks, Mark.
I'm not going to do too much introduction. I remember meeting Jennifer at the Media Lab. I've been tracking all the cool stuff she has been doing. I know she got grants doing stuff with fabrication. And I love the title, Expressive Computation. Okay, so I'm going to shut up and let Jennifer take over and tell us all the cool things that she's been doing.
Deal.
Great. Thank you so much, Ellen, for the introduction. And thanks, everyone, for inviting me to speak at Atlas and for coming to the talk. Today, I will be talking about my research in integrating computation with manual and physical production. Before I dive into that, it's useful to go in a bit to talk about kind of the big ideas I hope to convince you by at the end of this talk, although I sense in some regards that I am among like-minded folks. First, I'm going to argue that computational and manual forms of production are not mutually exclusive. And second, I'm going to argue that by understanding traditional makers, we can develop impactful and future technologies. So these are two really core themes that are going to run out throughout the course of what I present today, and I'll revisit them during the talk. Before diving into this topic, I want to briefly touch on the context in which I conduct my work. At UCSB, I direct the Expressive Computation Lab, which is a lab that is located under two departments within the College of Engineering, Computer Science and Media Arts and Technology. And in UCSB, I advise and collaborate with students with backgrounds across engineering, art, and design. And this variety is reflected in the range of research and methods that we engage in. So just give a small sample. Many students in my lab develop software tools for computational authoring. This is work in progress by the student Sonia Hashem. She's building a system called AIMS, which enables motion graphics designers to use hand-drawn vector paths to procedurally animate vector geometry. Much of the work we do in ECL requires understanding professional practice, and Sonia's work with AIMS is a reflection of that. She developed AIMS in part based on interviews she's conducted with professional motion graphics designers, and the approach she's using here reflects the broader human-centered design ethos of ECL. ECL is concerned with the physical as well as the digital, and we conduct research in novel materials and workflows for digital fabrication. One really great standout example of this is work that Mare Hirsch has conducted for her dissertation, where Mare has developed a 3D printing method using sodium acetate crystallization. These videos show how Mare has refined this method to support 3D printing at a rate that's faster than traditional forms of additive fabrication and in geometries that are not feasible with traditional forms of additive fabrication. While ECL's focus is largely on researching novel tool development, many students also build artwork. Here you can see a dynamic soft robotic sculpture that was created by PhD student Samuel Bourgault. And creating works of art is really critical to elements of what we do in ECL because it provides students with the opportunity to examine the affordances of computational media while engaged in the process of making. So here Sam is exploring how kinetic properties of soft robotics can support new forms of sculpture that resemble the human body. And then lastly, we also do a lot of work engaging in outreach with local communities. These images are from a recent workshop led by the PhD student Ashley DeValle with 60 middle school students in the Santa Barbara Junior High Science Program. For this workshop, Ashley collaborated with middle school faculty to build a curriculum that introduces students to procedural design using the P5.js programming language and computer-controlled pen plotters. Outreach activities like this are an important way for us to build partnership with experts and community groups that in turn can foster future research opportunities. and I'll discuss the importance of these partnerships later on in my talk. So the work we do in ECL is extremely varied, but it's unified by an emphasis on computation as a medium for making things, which brings me to the focus of my talk today. Computers increasingly shape both how and what we make, and different computing paradigms, both established and emerging, offer creators new ways to think and new spaces to make in. Expression within any given computing paradigm is mediated by the design and structure of computational tools. And by computational tool, what I mean is any tool that enables the creation of work through a series of rules, models, or instructions that can be maintained and executed by a computer. So computational tools can encompass anything from symbolic programming environments and parametric CAD to automated algorithmic filters and even CNC machines. Like any tool, computational tools both extend and constrain the capabilities of different people with respect to their implementation. So for example, creative coding languages like processing allow artists to create dynamic work, and they also require people to work through a symbolic description of the work. The process of building and designing computational tools is challenging. Part of this challenge stems from the nature of human production. Different people make different work in very different ways. The key properties of human production are difficult to define, incredibly complex, and often steeped in tradition. And just to talk about this point a little bit more, the role of making traditions is really hard to address in a 40-minute talk. But this quote from Mark Churchill, a ceramicist we're collaborating with, evokes some of the key elements. In describing his attitude towards high fire ceramics, Mark emphasizes how his motivation for pursuing this work is tied both to the material qualities of the process and their ability to replicate aspects of natural phenomena. And these factors shape both what he makes, but also his motivation for making. It's also difficult to make computational tools because computation itself is constantly changing. New platforms are regularly emerging as existing platforms are reshaped or rendered obsolete. And the rapid change of computational platforms can in turn shape attitudes about using computational tools. In particular, it can incentivize novelty and the rapid adoption of new techniques. This idea is illustrated in a quote from an interview I conducted with open source advocate and media artist, Chris Coleman. And Chris cited the example of convolutional neural networks as a technology for image generation to describe how he and other artists engage in a race to find the edge of emerging platforms as soon as they are pushed out. Lastly, computational tools are hard to build because computation itself is a brittle medium at times, and it requires the correctness of low-level elements to function. So this structure can limit the adoption of domain-specific interfaces and interaction strategies, and also encourages developers and designers to build tools as standalone siloed packages in many cases. Software applications in particular are extremely siloed, which can in turn limit workflows with these packages. This idea was embodied in comments from the illustrator Mackenzie Schubert, who we spoke with, where he described how the siloed structure of visual design tools created by the same company could restrict his ability to work between them and iterate quickly. And he expressed his desire to work with technologies in which subcomponents were modular and malleable. The creative opportunities of computation paradigms, contrasted with the restrictions of existing computational tools, suggest the need or opportunity for new methods to inform computational tool design and implementation. And that's really centered on the objective of the work that I do. So broadly speaking, the objective of my research is twofold. First, by supporting creative practitioners from domains that are often considered outside of computer science, including art, craft, manufacturing. My goal is to help people engage in computational production through systems that align with their existing knowledge, skills, and values. And in equal measure, I seek to understand how knowledge from established making traditions can lead to new groundbreaking computational technologies. I approach this work by systems engineering complex working interactive systems that let me test specific ideas and hypotheses on how computational representations and interfaces can enable creators to integrate core affordances of computation with practices from manual and physical domains. I work to identify alignments between domain-specific forms of manual or physical production and computational affordances, and then develop tools that embody qualities from both spaces. These alignments can be demonstrated through work created using systems I've built in my research, which is often work that blends computational affordances with traditional affordances and physical materials, but also seeing evidence of stylistic diversity from different people using the same system. It's also embodied by the experience that artists have using technologies that I've developed. So to give one evocative example, this is a quote from the artist Kim Smith, who's an oil painter, describing how her experience using a system from my research was similar to her experience working with oil paint. She described how she could start with a blank canvas and then explore to find something, and described how this process resonates with her experience working in paint. Methodologically, my work follows a cycle of development that draws from methods in human-centered design and design-based research, but emphasizes the production of functioning technological systems. So new computational systems are motivated by an understanding of professional making practices, developed by people with experience in both artifact production and engineering, refined through practical application and making work, and evaluated with practitioners based on the diversity of outcomes they enable. And this process subsequently motivates future systems. So let's take some look at a concrete manifestation of this process. And I'd like to talk about some projects that actually tackle some of the challenges I've identified. I'm going to talk about two projects within two different research avenues I'm currently engaged in. First, I'll talk about work in integrating manual creation with computer programming through domain-specific programming environments. And then I'll describe research in investigating computational fabrication through the co-production of computational technologies. So thinking about blending programming and manual practice, programming is a powerful tool for creation, as many people, probably everyone on this call is well aware. And while the creative applications of programming have broadened, actual approaches for writing code remain relatively narrow. To explore this idea, I've conducted extensive interviews with artists and designers who work with code or choose not to work with code, to focus on understanding how programming tools support or hinder their workflows. And there's a lot of information here, which I'm happy to talk more about. I'm gonna just touch on some key points, citing some quotes that really illustrate dominant themes in this work. So in examining the practice of visual artists, a common theme was the importance that manual artists placed on the direct connection between their hands and their work. This quote is from Chantel Martin, a visual artist who creates large-scale drawings and murals, and she compares her experience of programming with her experience drawing. She describes how programming lacks gestural and physical qualities of drawing, and contrasted the process of actually writing code with her drawing process by stating that she's very head-to-hand when she's creating. In illustrating this point and talking about a manual artist, I think it's important to note that I also spoke with artists who primarily work with code. And surprisingly, many of them also expressed frustration with the consistent aesthetics of procedural tools, contrasting them to the variation that's possible with manual expression. So the understanding of the power of programming as an expressive tool with the limits it poses through manual practice led to a specific avenue of exploration. How can I develop programming environments that support the integration of computational expression and drawing by hand? One insight I had in exploring this question was drawn through the work of programmer artists whose work involved a degree of manual expression and procedural production. And a prominent theme in looking at these artists was that people created their own software tools to let them combine drawing by hand with procedural styles or effects they had designed. This is one representative example, which is art created by the artist Eric Natsky, where Eric develops custom software that enabled him to draw freely with the stylus, while the software modifies the color and quality of his strokes, referencing different input data. So this insight led to the development of a system that I call dynamic brushes, which is an environment for personal drawing tool creation. It enables manual artists to create ad hoc procedural tools that transform manual drawing input. Dynamic brushes is based on an interface that's divided between a pressure-sensitive tablet and stylus and a desktop monitor. The artist uses the tablet to author artwork with the selected behaviors that they've defined in the desktop programming environment, which is a visual programming language where artists can drag out components and use them to author brush behaviors. Programming in dynamic brushes is structured around the creation of brushes, as I just alluded to, which are interactive drawing objects that correspond or that respond to manual input from the artist. Each brush has properties that define the style and geometric transformation of its strokes. And the programming model is centered around three core constructs. The first is property mappings, which are declarative mappings between input data and brush properties. And the primary form of input data is stylus properties, but mappings can also use generators as input, which are data types that produce a sequence of values corresponding to a given function, like a sine wave, for example. Mappings are organized within states. States describe collections of mappings that hold true when the state is active. And then event-driven transitions enable state change. Transitions can occur on a variety of triggers, including stylus events, geometric events, and intervals of time. And individual transitions can contain actions, which are called once when the transition occurs. And I'll talk more about that in a few slides. So the use of generators in dynamic brushes enable conventional digital drawing brushes to be converted into unconventional ones. For example, a brush that modulates the scale of the path with a square wave generator, creating an undulating pattern. This similar approach enables simple programs to create diverse outcomes by mapping generators to different properties. A simple stylus path can produce modulations in color, weight, and other stylistic properties around it based on the nature of the mapping. One of the most powerful aspects of programming is that it can be used to perform multiple actions simultaneously, leading to the production of intricate generative artwork. And dynamic brushes enable similar effects by using one brush to instantiate new brushes. This is facilitated through the spawn action, which is a method that enables a brush to generate a set number of instances of any other brush behavior, including its own, when a transition is executed. Spawning enables artists to use automated brushes that augment manual strokes. So for example, this drip brush was created entirely in dynamic brushes. And there's a lot to unpack with dynamic brushes, but I want to cover some future work that was inspired by this system. So just touch on a few examples. We used, and I'll briefly also talk about the evaluation of dynamic brushes, but it's a also pretty extensive topic. We evaluated dynamic brushes through a 2-week study with professional artists to understand how it performed in extended practice. This is a theme I'll continue to return on in later projects. But just to touch on a few outcomes, one thing we observed was participants using the spawning behavior to create brushes that made multiple marks progressively with different variations in the design. So here an artist created letter forms with brushes that created jitters and different aesthetics in the spawned brushes that were generated. And he used this to create an animated alphabet transitioning between different brushes that different drawn objects that were generated with his different brush behaviors. We also looked a lot at the process of working with the dynamic brushes system. And one kind of standout point to highlight is that artists in our study attributed their success in learning the system to the familiarity of the drawing interface, because it resembled tools that they were previously accustomed to. They described how this provided a comfortable starting point to explore some of the more challenging aspects of the programming environment. So this brings me to a critical point I want to emphasize with dynamic brushes. It is a symbolic programming tool, just one that uses a visual programming language. And while visual programming can offer more approachable entry points to some aspects of programming by limiting syntax errors, it's still subject to many of the challenges programmers face, namely understanding and debugging the connections between code and output. And these challenges were definitely present in our initial studies with dynamic brushes. So recognizing the challenges symbolic programming, visual or otherwise, presents when working with visual and direct interactions, we sought to build on dynamic brushes to build methods to aid in helping visual artists understand their programs. And we hypothesized that developing methods to show explicit links and visualizations of program parameters in the context of in-progress artwork might be a way to aid artists in understanding computational relationships while they're engaged in drawing. To test this idea, we extended the existing dynamic brushes system with specific program inspection and control tools. We entitled this revision Demystified Dynamic Brushes, or DDB. And this work was led by PhD student Jingyi Li and conducted in collaboration with researchers at Adobe and Stanford. So DDB builds on dynamic brushes with visual inspectors that lie on top of artwork and show otherwise invisible parameters like stylus input paths or brush properties, which are aimed at helping artists to reason about their programs. Numerical labels appear next to the artwork itself as artists are working, which means that artists don't have to interrupt their drawing process and context switch into reading a table of values, in contrast to more conventional debugging methods. The visual inspectors in DDB are supported by a direct selection feature, which lets artists touch elements of their artwork to jump to the program state at the point at which the artwork was drawn. And then these features are augmented by DDB's looping function, which is designed to let artists focus on exploring and quickly changing values while they're engaged in the drawing. So with looping engaged, artists can get immediate feedback about their brush changes while holding the stylus input as they change properties in the dynamic brushes program. DDB also includes more traditional code stepping in the visual programming environment, and this is designed to build on looping and direct selection, but provide a more slower and methodological inspection of program parameters in a manner that's similar to methods from traditional debugging tools. So far, I've primarily discussed systems that focus on visual output, but it's important to note that computation is remarkable in part due to its ability to blend different disciplines and different modalities of output. This is something that we've also explored by building on the work of dynamic brushes. Sorry. Specifically, we were interested in extending the idea of supporting expressive multimedia art creation by enabling artists to use manual drawing to express themselves across different modalities. Work by my current student, Sam Bourgault, directly explores this idea in her system, Megafauna, which is a drawing-based environment for audiovisual expression that was inspired by live coding. Megafauna is designed to enable the real-time production and automated synchronization of hand-drawn animation and sound, as well as the control of audiovisual parameters using exclusively a sketch-based graphical interface. And Sam presented this work at the Visual Language and Human-Centered Computing Conference in 2021. Just to go through some of the ideas of Megafauna, all operations are specified through drawing and direct manipulation. Artists pace animations in their work by drawing timelines of desired duration. And then once they've created a timeline, they can begin creating animated sequences by hand. And each frame of the animation is automatically mapped to an audio synthesizer, which triggers when the frame is activated. To modify the sound parameters or the frame order, an artist can draw mapping functions in sequence control graphs, which enable them to edit the sonic properties of an individual animation. And artists can also procedurally duplicate a sequence and specify the amount of copies on the screen through the act of drawing. Artists can also control individual parameters of copies or change the interval of time between each copy through the control graphs, creating harmonies or offsets in timing. An artist can also use drawing by erasing to mute elements of the sequences to further control the playback of their work. And I appreciate the laugh. This is something that we're really excited about in our work is building tools that are not just powerful, but delightful and playful. So work on Megafauna is continuing to progress. One thing that I'm really excited about with this work is the way we're continuing to evaluate the system. At present, Sam is using the tool to design and execute a real-time live performance in which all elements are generated live. And she's evaluating the performance with a panel of experts with backgrounds in live coding, analog performance, and animation. And this is kind of a feedback loop between authoring creative works and building systems that are supposed to be designed for certain forms of creative production. So work's still in progress, but the work with Megafauna also offers a way to reshape how we might think about designing computational interfaces for different levels of creative practice and different kinds of audiences. At an initial level, it suggests opportunities for systems researchers to develop new interfaces and representations that work across modalities that are appropriate for specific audiences. For example, a music composition tool targeted at visual artists. At a secondary level, it suggests the opportunity to research platforms aimed at supporting collaboration across different disciplines, like meta interfaces in which a domain expert can build appropriate representations for a collaborator. And this could be similar to how character riggers in animation set up expressive interfaces for animators, but we could broaden this idea to multidisciplinary domains. And finally, the third level, it offers the potential to consider how domain experts are best positioned to develop interfaces that fit specific modalities they're working in. This suggests the opportunity for research in how we help people create and use computational representations and interfaces that best fit their workflows. And this third area is one space that we're currently engaged in research in. So specifically, in collaboration with researchers at the University of Washington, we are examining the workflows of digital manufacturers, designers and makers who use digital fabrication to support the low volume production of goods. This is work that is supported by the National Science Foundation. And we're specifically looking at the ways in which their workflows are shaped and limited by existing computer-aided machining workflows. So thus far, we found that digital manufacturers are limited by the design of fabrication and software tools that isolate each stage of the production and impose prescribed design methods. Our explorations of existing practice have suggested new opportunities for software development support tools in digital fabrication that enable creators to develop program representations to support nonlinear workflows between physical and digital media. This work is very much in progress, but we're excited to explore and currently engaged in machine control systems that support interactivity and responsiveness for manual intervention in the context of pre-designed geometries. Computer-aided machining approaches that enable toolpaths to be described through manual demonstration. And toolpath representations that can dynamically adjust for different machines and scales. So when I started this talk, I began by arguing that computational and manual forms of creation are not mutually exclusive. And my research initially in building programming environments that combine manual creation and computational expression provides evidence to this point by illustrating how tools that integrate computational and manual making can expand the expressive potential of computers by preserving manual skill. And now I want to turn to my second argument, just to remind you that by understanding traditional makers, we can develop innovative and impactful computational technologies. To talk about this, I'm going to discuss some work I've done in computational fabrication investigation through co-production. So what do I mean by computational fabrication? Computational fabrication combines computational design with digital fabrication. A form is designed by writing a program and then constructed at least partially via digital fabrication machines to produce physical artifacts. In this case, a 3D printer. Computational fabrication has been explored primarily in the context of engineering research and industrial architecture, but it's highly relevant to other communities of practice. Specifically, many traditional crafts already involve algorithmic construction processes. And as digital fabrication machines become more accessible and diversify, they are increasingly compatible with craft materials. The alignments between computational fabrication and physical craft suggest opportunities to broaden participation in the professional application of computers, specifically by building workflows and technologies for craft production. Simultaneously, I believe that understanding how digital fabrication can be applied to craft practices with long traditions has the potential to lead to new innovations in computational fabrication as a whole. To kind of get at this, there's kind of some key challenges to get at this idea. So as some of my prior work has showed, building new computational tools can be directly enhanced by an understanding of specific forms of making. But key qualities of physical craft are often difficult to understand through observation or verbal discussion alone. So many craft disciplines are defined by tacit knowledge, and many forms of craft artifacts are intertwined with complex cultural factors. So in the interest of pursuing this research direction, I believe it's important to explore both how elements of traditional making are absent in the use of emerging technology and what approaches we can use to blend technologically supported practices with traditional ones. In many cases, physical making is best understood by actually engaging in the making practice. Outside of craft, or traditional craft, students, for example, learn a great deal more about how to create designs for 3D printing when they have direct access to a 3D printer. And this was an idea that was even more underscored for me over the last 2 years when, like many of you, I was teaching physical making classes remotely, in this case, digital fabrication. So the idea that making can inform the design of tools is an idea that I build on by pursuing the development of novel computational fabrication technologies through collaboration with craft professionals. And I'm going to briefly touch on some foundational work I've done in this space before talking about future work. This is work that I did in collaboration with Amit Zaran, looking at the integration of computational fabrication in the craft traditions and practices of people from Namibia. We conducted a workshop in Namibia with expert jewelry makers, which was particularly aimed at examining how to broaden the context in which computational design and digital fabrication could be evaluated as tools. Our collaborators in Namibia have a long tradition of decorative craft in the form of ostrich eggshell jewelry. And historically, this jewelry was played a role in gift giving, but today the San are professional makers and jewelry making is one of their primary forms of income. San jewelry production centers on the hand production of beads and the weaving of them in complex configurations, but they also regularly incorporate mass-produced jewelry components and use modern fabrication tools. Our objective in collaborating with the San was in part to understand how technologically supported making could be enhanced through a better understanding of their making practice. And the method we chose was to conduct collaborative making research on site with the San craftspeople. We chose this method both due to the challenges of working with the San, in particular, our relative lack of knowledge, despite initial visits around their craft traditions and methods, but also broader substantial cultural differences and linguistic barriers. However, this method also posed its own challenges in that we had to adopt a rural fabrication setting and use irregular natural materials in a fabrication process. And these were productive challenges, as I'll show. So we used computational design as a means to extend our software and fabrication tools during our work in Namibia with the San. Specifically to machine the irregular curved ostrich eggshells, we worked with the San to create a CNC milling workflow that enabled us to both etch and carve designs with a high degree of accuracy in the eggshell material. We represented this workflow as a generalized procedure in the Grasshopper visual programming language, which made it easy to adapt it for different designs, for variations in material and technique, and explore changes throughout the collaboration. This translated and is evident in the range of techniques we developed with the same material in a relatively short period of time, from basic engraving to more complex subtractive fabrication, to the ability to create high precision and low volume multiples. We use these methods to collaboratively produce 60 artifacts over 40 hours total of collaborative making activity. And just to touch upon some of the facets of these artifacts, the integration of computational design translated first and foremost to immediacy and exploring alternatives. One thing we focused on was creating these eggshell pendants, and you can see a wide variation of approaches that we developed in collaboration over a short period of time. We also examined using parametric design to explore variations in pendant designs specified by our collaborators that were repetitive and symmetrical. And this enabled us to create variations in this space. And then we were also able to develop custom software to create low volume, high precision modular components out of the natural material that we were working with. So this led to modular outcomes that could be reworked in physical production, gradients of beads, press fit kinetic parts, and also interlocking press fit components. Our ability to produce these variations was the result of being able to leverage the combination of computational design and digital fabrication to explore forms that were compatible with the constraints of the material, but also to get direct feedback from the San on what methods would be effective and not effective in actually producing artifacts. There were key limitations in our efforts and our approach. The biggest one was our use of traditional computer-aided design software, where we were expressing designs through a series of abstracted design operations to produce a finished work, which is really at odds with how the San worked in their design process, wherein their process was dictated largely by the concrete, and they explored variations by iterating over available physical components as opposed to thinking in terms of operations or working in terms of operations. which is a context that's been documented in many other craft forms of production. So there was a lot to take away from this work, but some of the key points that are relevant for the work that I'm discussing going forward was that we were able to use CAM CNC programming and parametric design, CAM CNC programming to support the custom machining of workflows with collaboration-specific materials. Moreover, parametric modeling enabled a rapid collaborative exploration and iteration of designs over a short time frame. But we also saw useful conflicts for future work in terms of conventional CAD geometry primitives and conflicts with physical design practices, suggested the opportunity to explore different approaches in supporting CAD approaches with concrete physical craft in this specific context. So at present, I'm actively building on the work that we did with the SON for a new, more ambitious research project aimed at looking at ways to blend computational fabrication with traditional rural ceramics craft traditions. And this work is done in collaboration with professors Leah Beakley, Manuel Montoya, Ted Hohola, and Tim Castillo at the University of New Mexico. It's work that's been supported by a National Science Foundation Future of Work at the Human Technology Frontier grant. We're still early in the phase of this work, but I want to share some initial outcomes and next steps. So it's been underway for about 6 months. And the model that we're taking builds on some of the same approaches that Amit and I took when working with the SON, but at a larger scale. We've begun our work by conducting studio visits with master ceramics craftspeople. And in these visits, we've conducted interviews where we focus on understanding the different approaches to manual ceramics practice that creators have, their attitudes towards technology, and how these factors relate to their business practice, specifically their ability to make a living and differentiate their work on the market. In tandem with and informed by these interviews, we've worked to explore the application of computational fabrication technologies in our lab towards the production of functional ceramics. This has involved the use of clay 3D printers, robotic extrusion, and other existing fabrication methods to build procedurally generated geometry in clay. And this process has revealed critical insights already for how computational ceramics differs from other forms of digital fabrication. So for example, it's demonstrated that it's much more productive to design for machine toolpaths rather than geometries, because this lets us take advantage of the unique plasticity of clay and productively recover from variations in the fabrication process. But both our interviews and our initial fabrication work are really primarily intended to inform the core aspect of this research project, which is collaborative design residencies with ceramics professionals. Through these residencies, our goal is to develop new computational fabrication technologies through co-production of ceramic artifacts that integrate qualities from both traditional and computational approaches. We've actually just completed our first residency call and are currently in the process of selecting candidates to begin work this summer, which we're really excited about and nervous about. And I feel like it's really important to mention here that our approach directly builds on work by one of Atlas's own, Professor Laura Devendorf, and we're really privileged to have her serving as a committee member for our residency selection. And we're really benefiting from her experience conducting residencies with artists in computer-controlled weaving. So going forward, I'm eager to investigate how collaborative making partnerships can inform the development of approaches that integrate cultural, economic, and technological concerns. So just to quickly wrap up here, I'm extremely, this work was motivated through work in craft and computational fabrication that's centered on the premise that understanding traditional makers can help us develop impactful computational technologies. And I see an opportunity for collaborative partnerships in particular as a powerful method to investigate not only how to combine traditional emerging forms of production, but to understand the impacts of these combinations in real-world professional practice. And I'm extremely excited to continue to report on where these partnerships take us in the future. And with that, I'll conclude. Thank you so much for attending. I'd like to once again acknowledge my collaborators at UNM, UW, Stanford, Adobe, and UCSB. And I'm happy to answer any questions for anyone who can stick around. Thank you so much.
Somebody's trying to.
The floor is open for conversation.
Yes, ask questions, comments. JP, go.
JP, say it. JP in Seattle.
Otherwise, I'm happy to go ahead with the first question while we're waiting. Can you hear me?
I can hear you, yes. Hi, Dan.
Yeah. Thanks for this really enlightening talk. I enjoyed it very much. I was wondering, so you mentioned a few times throughout your talk in your work with the Dassault and with the ceramicists now that that the traditional CAD interfaces that you're using are for you, don't exactly work with your collaborators or lead to problems, and that you're excited about developing new tools there. And I would love to hear what's your hunch or insight on what direction that would go. Like, are you seeing this towards like physical interfaces or more like different computational tools like drawing and other?
Yeah, so maybe I can speak about this directly in ceramics, because maybe as it's indicated by my slides, that's sort of where my brain is at mostly these days. It depends so much on the specific craftsperson and context. And so I just want to be clear about that we're not trying to represent craftspeople as a monolith in any context. And among even what I've described as traditional craftspeople, there's a ton of variety in their experience with digital and computational tools. So, one kind of main question in thinking about alternative interfaces are for craftspeople who are already working with CAD in their process, which many of the folks we've interviewed actually do, or are they people who are not interested in that element? So if that's been like an interesting aspect is there are people who I would describe as traditional ceramics craftspeople who spend time in CAD and are comfortable doing it. That being said, most of the opportunities relate specifically in ceramics to computer-aided machining control and the process that takes. So unlike traditional FDM printing of like ABS material or other plastic material, ceramics printing is much faster and also, as I mentioned, more plastic, which both gives it less predictability, but also greater flexibility. One of the spaces I'm most interested in CAM is live tuning mechanisms for controlling properties of the machine operation as the geometry is actually being fabricated. This is something that is useful to adapt to changes in clay material or changes in what would be considered, I guess, errors or surprises in the printing process. But it also fits more with what we've observed people who are already working with 3D printing of clay actually engage in their process. They're tweaking, tuning, making adjustments as a machine is working, as opposed to having CAM be a totally separate process that is executed automatically. So there's really rich opportunity for thinking about what's the interface for enabling people to adjust machine parameters and predict some outcomes for that process in the context of clay fabrication. That seems attractive for some of the folks we've talked to who are fundamentally not interested in being in front of a computer, in that it provides an opportunity to center some of the design activity around working with the machine as opposed to creating a digital design first in a software tool. So hopefully that gets at some of the ideas. I think there's a lot more opportunity in this space, but we're still early in the process.
So when you say tuning, do you mean like there would be like a bunch of knobs and faders, kind of like a mixing console that would let them like adjust the machine in real time, as opposed to going to a computer and?
Yeah, I mean, I think it can be knobs. It could also be, I don't think it has to be physical elements necessarily. I think the difference is the focus of the work is the piece that's being printed. Like really, that's the biggest decoupling we're getting away from, is the information you're creating as a series of steps or operations. The models and geometries you simulate in CAD don't have a ton of bearing or are really unequipped to represent the possibility of effects you can get through machine behavior and material behavior interacting. So I'd say it's a combination of interface for adjusting and controlling machine parameters, but focusing on perceiving the output through what's actually happening in the fabrication space.
Thank you.
Yes, JP, go ahead.
Thank you. Yeah, wonderful talk.
Thank you.
Stunning, beautiful slides too. You can read the question that I put in the chat faster than I can say it, but just the color commentary is a lot of the talk for me really was about, you know, the head and the hand and connecting the head and the hand. And I'm interested in the heart. And so asking about the uncanny was, how does this work affect feelings? Because you're pushing envelopes both for the developers and for the artists, presumably.
So I think this is such an interesting question. I can really only speak from my own experience. And this may sound a bit contradictory, but as someone who is really focused on, is probably evident in my talk, all of the rich expressive power of code and computation, the most like impactful element of doing this work, particularly with folks like the SAN, or with being able to observe master ceramicists at work in their studio, has been like just really grappling with how limited we are with computers right now, in contrast to these histories of making. Like there's just so much knowledge and skill that I am excited to get at, but I'm really humbled by the scope of knowledge that exists in these domains that we're exploring. And so like that's something I'm also trying to bring with me in this work, is being excited about the potentials of introducing computation to established practices, but also I think like humbleness is the right word, or productive skepticism about what are the real benefits that new tools can offer in these spaces that go beyond, you know, interesting novelties. And so that's why I'm most excited about these partnerships, is it's an opportunity to be critical about these types of integrations as well. Yeah.
Thank you.
Jessica.
Hi, this is probably going to sound really bizarre. So when I think of tools, I think of the willingness of the user and that threshold. I think you talked about that, like you had different levels of openness to people adopting your tools in your different environments, whether it was with artists, which are musical artists, beat makers, or people who draw. And one of my thoughts is like, do you see, as well as skill difference and comfort level, do you see age differences? And I'm with you, like anything can be used artistically. And I'm thinking back to when I did environmental consulting work and going to a landfill where we had to do some cleanup, and watching this man operate a tractor like it was an extension of his body. It looked like a dancer on the hills, compacting the hills. And so I guess there there's an observation that, you know, I think there's a moment, a critical moment that people become interested. And maybe it's related to Sis Mahali's work around flow, like you just add an incremental level of challenge and creativity and they become interested. And what are you seeing with that? I don't know if I made any sense.
Yeah, so I think your question around age is something we've seen. You know, we're still at the early stage of analyzing the interview data we've collected, and we're still in the process of doing more interviews, but there's been some initial emerging patterns around some of the older artists being interested in things like clay 3D printing or computational design, but stating like, this is something that younger generations will adopt. Although I'm cautious to take them at their word in some cases, or I guess like it's still unclear to me if that's a reflection of their actual interests versus kind of larger trends around ideas of who can adopt emerging technologies and who can't. So to give a very anecdotal example, we spoke with a master ceramicist who kind of in our conversation was interested in these tools, but also said like, yeah, this is something that probably my apprentice should explore. But then later on, he reached out to us being interested in coming to our lab and collaborating. It just, so there's some tensions there. The other challenge we're encountering, which relates to your question, is how do you know, just as kind of the flip side of the challenge of how do we understand key knowledge in craft production, there's a flip side of how do we communicate key affordances of computational production to people who don't have direct experience in working with these tools. And that's been something that's like another area of work that we need to do better on going forward. And hopefully our residencies will inform. We've primarily focused on, you know, showing artifacts we've created in our labs to professional practitioners to get a sense of like geometries that are possible, designs that are possible, techniques that are possible with computational fabrication. But it's imbalanced because we're not ceramicists, we're researchers. And so our approaches are just at a different skill level than them. And so, you know, like one maybe future direction for this work is thinking about, you know, rather than us being the collaborators, there are some amazing craftspeople who work exclusively in digital fabrication or extensively in digital fabrication, and thinking about contexts for dialogue and collaboration between digital craftspeople, for lack of a better term, and traditional craftspeople might be a way to get at some of that, but we haven't gotten that far yet.
I'm wondering if you were to, you know, your expertise is the computational world, right? So if you were to consider yourself like the craftsperson whose expertise is the craft, you just have different crafts and kind of reverse engineer, this is what I'm going through as a challenge to understand, and apply your challenges to theirs and vice versa, if there's like this beautiful middle ground. Just a wondering.
Yeah, I think it also might relate a bit to thinking about education, like who are the students we bring into computing programs, which is something that's really exciting about the Atlas program and CU Boulder as a whole is the variety of people that are brought together. But I guess I see opportunities for thinking about education around computing and craft in a different way, I guess.
Hi, this is Chris Byrne. I have a quick question. It's probably a dumb question, but it's just something I wondered about, particularly as you were talking. And in particular, I sort of tee off sort of my primitive understanding of the chicken and egg relationship between, both in biological systems and robotics, between motion and intelligence. and how motion, like anybody who's ever tried to learn a musical instrument, understands that relationship, and other things. And my dumb question is, I do feel like computation is still behind biology, thankfully, and we almost have to sort of accommodate the computer as opposed to the reverse. But one of the things I was wondering about as you were going through this, because I thought your talk was remarkable, is it possible, are you aware of techniques or technologies where emotion could generate the code? So for instance, you know, as a robot was going through something, it would actually generate the code that the robot was improvising, or that the craftsperson was implementing, just the movement of their hands and so forth. And you know, when I think about it, like for instance, you could take the same piece of musical notation and several different people would sound differently playing the same thing. And so I kind of wonder about that ability to go from the biological motion to code generation in addition to the code and the motion, if that makes sense.
Yeah, it does. It reminds me of a student project in one of my classes where they built a tool for color palette selection when you're drawing, using kind of sentiment analysis of a person's facial expressions to pick the colors automatically for their drawing. So I guess that work would draw a lot from approaches in effective computing, trying to computationally predict and interpret affective states or emotional states of people. That work is incredibly exciting. I think it would be such a cool space to explore. In some ways, it presents, if you put aside some of the real challenges around effective computing, which I'm definitely not equipped to talk about, the idea of doing any type of automated mapping between some input and some kind of output brings in really challenging questions around how you negotiate that mapping and who it's going to benefit and in what context, which is really at the core of a lot of the work that I do. So we've tried to approach selecting forms of automated mapping that reflect or don't overly limit key forms of expressiveness in practice. I actually don't have a great understanding of the degree to which emotion plays a role in different craft practices from people we've talked about. And I think sometimes emotion might get correlated with elements that are maybe more related to the tacit space of things like physical feedback or gestural motion through space or proprioception, which are incredibly important, but maybe not emotional, depending on the person who's working. So more broadly, I guess I would take your question and think about if this is a direction that somebody we were working with was interested in exploring, you know, what would be the process of them determining the types of mappings they would want between effective signals and types of output, and how could we support that process? That seems to be where I'm most interested.
Yeah, you know, as I'm thinking about the question and your response, I guess a way for me to kind of bookmark the thought is sort of, you know, an increasingly sophisticated form of motion capture, in a sense, I guess, is what I'm kind of intrigued by. In any case, the work and the talk are both remarkable, and I just want to acknowledge that and thank you.
Thank you for your question, and thanks for saying that. Yeah, I see your comment, Michael, and definitely we're in a high state of anxiety at all times when we're printing, in many cases, because of the risk to the print involved. So we'd have to do some throttling on that.
Hi, I have a question that when you present those kind of tools to the artist, an artist still needs some kind of degrees of the computational thinking to use those tools. So I'm wondering, is there any insight from your research that how artists combine their imagination with the computational thinking.
Yeah, so I can speak around that, I guess. One of the really interesting things about the dynamic brush, the initial evaluation of dynamic brushes, is that we worked with artists who didn't have prior programming experience. And in this case, we just worked with them for a period of 2 weeks. And one of the interesting things about that, still relatively short, but somewhat extended evaluation, was over the course of the 2 weeks, they not only learned how to use the dynamic brushes system, they learned a better understanding of some of the general properties of things like instantiation or looping or data structures through the course of doing that. And so actually, in addition to them being able to produce outcomes, they were better equipped to describe alternatives to how we had represented these approaches in dynamic brushes based on their existing practice. So I think there's a lot of variation in how different artists think about their creative objectives with respect to different computational systems and also just general computational representations. But I do see an opportunity to use collaborative development as a way to build knowledge for people that we need information from around computational affordances and get better insight into how to re-envision those as they develop an understanding of how to work with them. It's very selfish on my behalf, but it's been an interesting phenomena that I've observed in some of my work so far.
Last call. I'm going to count to 10 silently. There you go, Jill Dupre, applauding.
Oh, applauding. That's before 10. Okay. Well, thank you, Jennifer. That was wonderful.
Thank you. I know now why I fell in love with you all those years ago. It's so awesome.
It's been such a pleasure to engage with this community, and yeah, look forward to continuing the conversation in the future. Thank you all for coming out.